Yeah. So matrix of lambda of S wherein like lambda times transformation of X is again the same as lambda times the matrix of that transformation. So these two are like direct result from the linearity of the transformations that we're talking about. I think they have given the proof here of that thing. Okay, they have not given proof. I think it's just very intuitive. If you work it out, you might get it. But okay, so and then there's this third property that they are talking about is basically like if T takes from U to V and then S takes from V to W, then obviously T to so basically if you do that transformation like one after the another, right? So that is represented by this S dot T. So you always read the transformation from left to right. So this means first we do a transformation through T and then we apply a transformation through S. So matrix of that two transformations in like net transformation. So obviously you can represent two like all of these transformations using, we are interested in knowing like what is a single transformation that gives us effectively these two transformations. So think of one transformation as rotation and then one as shearing. So what this represents is like the combined matrix of those two transformations, so that we can have both of them with a single, in a single go. So this is given by this. And I think this should be very intuitive if you have watched those lectures. Can anyone like just comment on why this is very direct result? Like matrix of the two transformation combined is equal to matrix of the whatever this is written. So matrix of first transformation multiplied by matrix of the second transformation. Like a small hint is basically lies in the fact that so we saw a way to multiply the matrices, right, by linear combination of the columns of the matrices. So that might be useful here. So can anyone take an attempt on this?
So when we multiply the original basis with m of t, we bring it to the new basis vectors, and after we multiply that with m of s, we get the final result. So if we multiply the two matrices, we can directly get the final.
I mean, sort of correct only. But yeah, I mean, see, essentially, if you talk about the intuition that we saw in those videos, is basically applying one transformation with another after another, right? So basically, see, okay, it's difficult to explain like intuitively. I think it's like first you apply sharing, you have that the matrix for that, and then so the dot operation between two matrices represents the same thing that we talked about, like the linear combinations, right? And that is what we essentially need. So that's I think that's the best explanation that I can give you without going into further details. But I think if you watch those videos, it should be much like, I think he gives us a very intuitive understanding of this. Yeah, I think it's composition of two transformation. Yes, is basically so the way we have defined this multiplication for two matrices, right, is exactly the same which we require for composition of two matrices. So that's that. I think that's the best explanation that I have for now. But I think if you look into those videos, it should be like more clear. Anyway, it's not that difficult. You can prove this like mathematically as well, so it shouldn't be a big deal. I think they are talking. So they are talking about transpose here. So they are. So transpose everyone knows, right? Just replace the, so when we build the transpose of a matrix, it's just replacing rows with columns. So 1, 2, 3 here is a rows. You can just write it in same order as columns. So that represents the transpose of a matrix. Now, what this represents symmetrically is something which actually I don't remember this. Like what this transformation represents of a transpose. Then yeah, so Parvez is saying something. First, we move the basis to the landing point of basis vector, and then move the vector to the next point. So yeah, I think yeah. So Parvez, I think that yeah. So I mean, essentially, that's the explanation of this question. So that's correct explanation. But Yeah, so I think we are talking about transpose here. So the geometric intuition of transpose is something which I don't remember, but I think just know for now, like this is one of the operations that I think that we'll study later. Then maybe we can look into that later. But just for now, it's just I think enough to remember that this basically just interchange of rows and columns is what a transpose is. And conjugate transpose is basically so not every matrix is, so when we talk about matrices that for which the elements are just a complex number. So then what you do is like instead also after doing like interchanging rows with columns, you also take the conjugate of that particular complex number. So remember the conjugate of complex number is like a plus ib is like a minus ib. So you just change the sign of the imaginary part, that's it. Okay, so that is called complex conjugate, and that is represented by a star. So when you see the a star on a sign, so that means like basically a complex conjugate. Sorry, uh, conjugate transpose. That's it. So if it is real numbers, then you see like the conjugate of real number is the real number itself, right? So that's so basically eh, just a transpose. Conjugate transpose essentially is like you just take the conjugate once you do the transpose. That's it. And so plus sign is also, so plus and star sign. I think these two represent the conjugate transpose. Okay, so that's what they are. And second, let me see what they have written here. So okay, this sign, guys, this sign represents the like outer product of two vectors or whatever like elements that we are talking about. So outer product is not just dot product of the vectors or something. It's a generic operator that you can choose to define in any way depending on whatever elements you are dealing with. So outer product of vectors is defined like corresponding like multiplication of elements and then summing of them. But this is a very generic sign. You can like just choose to define your own outer product when you're talking defining a field or anything. So yeah, so this whenever you see this, you can just safely assume it's a dot product, at least for the context of vectors that we are talking about. Now this sign is, I think, basically Rn, which is will represent a dimension of the vectors that are involved. I'm not very sure what they have written here. Assume f is equal to c. Let's just skip it, I guess. Okay, so invertible maps and matrix. Okay, so inversion is basically whatever transformation you have done through matrix, right? You want to have another function which can take the final resultant vector and map it back to the original vector from which it came from. So that's basically the inversion that we are talking interested here. And invertible maps are essentially those things only. So you apply any transformation, any other arbitrary function that can basically reverse that transformation is called T inverse, right? So and when we say reverse, the different like the definition has certain requirements. So those requirements are just T inverse of T of V is equal to V. That's it. I mean, this is very straightforward when you see it is written, but yeah, I mean, this is what we need from that inverse transformation or invertible map. So invertible map is general term when we talk about any linear transformation. So like I said, matrices is one of the tool to represent a linear transformation, but there are a lot of transformations that we're generally interested in. Okay, so that's why there's a generic term called invertible map. So if you take any arbitrary transformation, if whatever things reverses that, that will be basically invertible transformation. Now injective and surjective is basically invertible. I think this is pretty intuitive, right? So injective meaning every element in the source space has at least is mapped to some element in the range. And surjective means like for every element in the range, you will find a unique, basically a unique thing that it came from. So the thing that was mapped to that particular thing. So if both of these properties are satisfied, that means like we can safely invert it, right? Because what inversion basically means is like for every element in range, you will find something that for which that particular thing was image of, right? So yeah, I mean, I think this basically defines the necessary conditions for inversion. Um, so this dot sign is basically T after this. You can read this as T after S. So essentially something like a matrix multiplication, right? So when we write A, B, C, where A, B, C represent a matrix multiplications, you always read it as like A after B after C. So you always multiply your vector with C first, and then multiply your vector with B first, and multiply vector with C first. So similarly, this means like first you have to apply the transformation, which is S. Second, then you have to apply the transformation T on that particular transform thing after S. Okay. So I think they are talking about linearity of inversion here, and they prove that if a matrix is linear, like transformation is linear, then inverse transformation would also be linear. So inverse of a matrix. Okay. So here they have written a square matrix A is invertible if there exists a square matrix B such that A dot B is equal to B dot A is equal to identity matrix. So identity matrix is basically one on every diagonals. So I mean, so this basically means like if you want to invert a transformation, and so you essentially have to find a matrix that if you multiply it by that particular transformation gives you identity matrix. So we will then we can say that particular thing is inverse matrix of that particular matrix. Can anyone like give an intuition like why this has to be a like identity matrix, like inverse operation? So A is mapping some no, this is not a scalar. This is basically like if you remember when we talked about field and like definition of field and definition existence of a dot operation, right? So that is that particular dot operation. In case of matrix, it's basically a matrix multiplication operation. It's not dot. So it's not element element. It's basically regular matrix multiplication that we saw.
It should be identity matrix because
Hmm.
I mean you are just inverting what the transformation that you just did. So if you multiply anything by identity matrix, nothing happens.
Yes, yes. Yeah, so that's one good explanation. So basically, like I said, right, if you're doing B and if you're doing A, the net result should mean like you did nothing, right? And you can only get that result like nothing is basically like this. Like if you multiply anything by identity, it's basically an identity, right? It's basically the same thing. Sorry. So the same property that we studied about in and when we discussed about groups and fields, right? So yeah. So okay. Inverse matrix represents the inverse of the corresponding linear mapping, that is TV. In a transformation, the basis vector is changed and transform back, we should get the same basis. Yeah, I mean, yeah, so that's a necessary condition, I guess. So I think what they have written is like matrix of the inversion is same as like inverse of a matrix of that transformation. So I mean, we haven't talked about like what is concept of inversion of a like this basically this operation like inverse of matrix, but essentially like this is the same thing only, right? So basically matrix of inverse transformation, and if you take a matrix and inverse that, so how to calculate inverse of a matrix, I think we must have studied that, right? So basically involves calculating some adjoint determinant. There was used to be some stuff, even I don't remember, but essentially that particular operation. Yeah, I guess I think I don't remember. I think Kramer's does ring a bell, but whatever that way of calculating inverse of a matrix is, that essentially is same as matrix of that inverse transformation. I don't know, like anyone can like does anyone remember how we used to do this like inversion of a matrix? Yeah, I think you can look it up, even I don't remember, but that's not very important here. The importance is like what I think is like these two things should match. Okay. Yeah.
I think you can have the matrix on one side and identity matrix on the right side.
Mhm.
Then by Gaussian elimination, convert the left side to identity and do
Mm.
the same steps on right side. Then the right side will become the inverse.
Yeah,
matrix.
I think that's so Gaussian elimination is what we used to do. So whatever set of operation we used to do on LHS, we used to do the same set of operation on RHS. I think if I remember correctly, Gaussian elimination is is reducing, is picking starting from the last row and doing some multiplication and subtraction so that everything changes to identity one row at a time, right? Something like that. Is that correct?
Yes, so you start from the first row and you make all the element in that column zeros. Like
Hmm.
for the first row, you will keep the first element as 1 by dividing, and then use that to make all the other elements in that column 0.
Yeah.
Then
So
from
whatever
second row,
you repeat the
yeah.
process iteratively, right? Yeah, I think so you can read that up. It's not like if you don't tend to use it, you tend to forget it. But yeah, I mean whatever. Uh, so essentially the concept was you just try to reduce everything to 1000, such that one only remains on the diagonal. Then whatever you have on the right hand side will be the inverse of the matrix, I guess. So yeah, so essentially these two things should equate. That's the thing that we're interested in, for like at least for now. So there are a couple of like properties of inverse, like inverse of a map, not just inverse of a matrix, inverse of like linear transformation. So it's basically this is followed from the definition itself. A inverse ka inverse is A dot B ka inverse is B inverse A inverse. Okay, can anyone tell me why this is the case? Like just like intuition based on the videos that you must have seen. And 3 blue, 1 brown.
So when we have A and B, first we are transforming with B, then we are transforming with A, and then taking the inverse. So in the inverse, what it will be backwards, right? Because
Yeah, so forget inverse flow. If you do A into B, right, on some vector, so that essentially means, so I always said it, read dot like whatever sign is there as A after B. So that essentially means is like you take a vector, you apply the B first, and then you apply A on that particular thing that you got. So if you have to reverse this thing, right, so you have to first go from backside, right? So something like a stack kind of a thing. मतलब जहाँ से निकाल, so basically you did things in some order and you have to undo the things, you have to remove the things from the top. So last में A लगाया तो सबसे पहले A को invert करोगे, फिर उसके बाद B लगाया फिर B को invert करोगे, so and so on, right? So whatever the operation that you did here, the reverse operation to get the original thing back. Okay, so it can be like yeah, so A inverse is basically like if you want to nullify the effect of A, you have to multiply that by A inverse, right? If you want to nullify the effect of B, then you have to multiply that by B inverse, right? So that's what we are interested in. So we are interested in inversing the whatever operation that happened inside this. So let's suppose A, B, C happened, then we know C happened first, and B happened, then A happened. Yeah, first and last row. Yeah, exactly. Same concept. Okay. 80 invertible is AC invertible. A transpose ka inverse is yeah, okay. So basically what they are saying is like if I do a transpose and then invert is essentially same as if I do the inverse and then transpose it. Now this property, I think this can be proved mathematically. इसका इतना कोई खास intuition अभी मेरे पास नहीं है, because transpose geometrically क्या represent करता है, even I don't remember very correctly, but I guess this is more like a mathematical result as compared to something which is intuitive, I guess. If anyone here can like knows some intuition, then they feel free to ping. But I think if I, as far as I remember correctly, like even I try to look into this, but this is mostly a mathematical result.
if A transpose is invertible, it means all of the columns must be linearly independent, right? So
Mhm.
So if we take the transpose, still all the columns will be linearly independent.
No, so see, so whatever. So one second. So what was your first statement?
So if it is invertible, it means that all the columns must be linearly independent, right?
And how can we say that?
Because if even one of them is linearly dependent on the other, then you can't take the inverse because the determinant will be 0.
Determinant will be 0 if basically the rank of that matrix. So basically the number of columns is basically more than the rank of a matrix. So if you're saying that if not all the columns are linearly independent, then that essentially maps to a 0 determinant, right?
I
Is that
think
what?
so. I mean, I don't remember, but
Okay, so let's just consider this case, right? So if one of them is not linearly, if it's linearly dependent on them, on one of the other vectors, then inverting that matrix. Once again, first of all, would that even represent a linear transformation? That's the question, right? So we are talking about the matrices that represent a linear transformation here. So, I mean, obviously, every matrix does represent a linear transformation, but let's suppose if we create a matrix in such a way such that, one of the columns is linearly dependent on like one of the other columns, then yeah, I think it should map it should basically map the I think determinant why. So this is very like an intuitive thing. Like why should determinant be 0? Because I cannot still see like if even if one of the columns is not linearly independent, then determinant is to be 0. But anyway, I think that result has nothing to. I don't think that has anything to do with explaining this. Like first we apply. So we can discuss that result later maybe. But what we are interested in here, so what they have written is like if you do the inversion and then take a transpose, then it's the same operation if you do the transpose and then take an inversion. So
so for equality, I'm not sure, but the statement that if one is transpose and it is invertible, then the A is also invertible. That one can be proved by this linear independence.
sorry, can you please repeat your last statement again? This is
So in that third point,
Ritesh, right?
yes. In
Yeah,
that third point, we can prove that first half by this determinant thing, and second half, I'm not sure.
But I mean, okay, so for those matrices and for which determinant is 0, maybe we can. But what about those cases when the
No,
determinant is
if the determinant is 0, then it is not invertible, and if it is not 0, then it is invertible, and it has all the columns have to be linearly independent.
yeah. So see, if the determinant is 0, that's then that's pretty much intuitive um, from the videos, I guess, right? So if you are mapping something to null space, you cannot recover that back, right? So that why that
Yes.
matrix becomes like like non-invertible, whatever that term is. Now, in case of non-zero determinant, what you are saying is what's the fact that you're saying that proves this?
That all the columns have to be linearly independent, right?
Yeah. Okay.
So all the rows are also linearly independent because each of them have one pivot in them.
I'm not very sure like how this particular thing. That
So
if
if you take a matrix and all the columns are linearly independent, then all the rows will also be linearly independent.
Why is that so? You're saying that pivot. So what? So what is the reason that you're saying?
So if we do Gaussian elimination on them, so each of them will have one pivot, right?
Okay, so I don't remember Gaussian explanation, the Gaussian elimination very well. So maybe I'll just read it up and then maybe I can come back to you on this. But I'm not very sure like how linear independence of columns proves the linear independence of rows directly.
Okay, I will Google and check if there is a simpler proof.
Maybe we can like look it up, right? So